Ой, сейчас мне нужно, что-то я болтала, мне нужно было подключиться. Сейчас, секунду, я. Okay. Now I would like to talk about press sheaves and sheaves, and we start with the example of standard example. Okay, we want to construct an analog of the continuous function set on a topological space in category theory. Let x let x be be a space with open sets. U sub x and for each u we have some function. Function f from u to r. And it is known that f is continuous if and only if it is continuous locally. And this means two properties. This means two properties. Property number one, we can form restriction f for subset v over u from v to r, and also the second condition, if we have covering u is covered by ui, and for each ui we have a function fi from ui to r, then continuous, of course. Then there is at most one function. Then there is at most one function f from u to r, such that if we consider restrictions over f on ui, then it equal corresponding fi, and also fi should agree on each intersection. Fi agrees on each intersection ui with g for I and g, and this condition means that continuous functions are uniquely collectible. Continuous functions are uniquely collectible. Okay, this is an important example. And now consider functor C from O of X opposite. O of X means the set of all open subsets of X is a set of is a category, the category of open subsets of X, and this category with arrows and arrows is just inclusions, is an arrow in this category. Okay, and we have a functor from this category to the category of set. And for instance, CU is a set of all continuous functions f from U to R continuous. Okay, and on morphism V to U, we have a map of we have a restriction of corresponding function from this to this, and if we consider some function f, then we just find restriction on a set V. Okay. Also, restriction is transitive. That is, if we have these inclusions of sets W, V, and U, then we have that F restricted on V restricted on W equals F restricted on W. This is natural conditions, and this is not a general definition, but useful example. Okay. In the same example, for property 2, we have, if we have a current and a family of functions fi, family of functions. This family defines an element of the product set. I should okay. It defines an element of the product set C U I from the membrane set I, and the assignments fi 2 fi restricted and also fg to fg restricted on the intersection. Define maps. Define maps P and Q such that we have the following equalizer diagram. Cu, product over Cui to by means of P and by means of Q to the products or of C of intersections UI and UG. This is just restriction. And for this diagram, we can consider limit, and this limit calls, of course, an equalizer, and this equalizer we denote in the following way. Okay. And the property 2, then property 2 can be reformulated, as the map given by these sums is just the equalizer of the maps P and Q. Is the equalizer of the maps P and Q. Okay. And also, if usually we have a sheaf of algebras over R, but not only sheaf of sets. And in this setting, we can reformulate this diagram in the following way. 0. We can consider the following exact sequence. Okay. Other examples of sheaves on a space X. Number 1, we can consider functor D with each D of U, the set of all functions continuous or not. And the second trivial example, functor I, with each I of u, the set of functions from u to the interval I. And the third example, this is a cross sections of bundles. Cross sections of bundles. Also, for example, sheaves of vector fields on M. Sheaves of vector fields on a manifold M. Sheaves of tensors on M. Okay. Also ringed spaces. That is spaces with a fixed sheaf of a sheaf of rings. And we now I want to discuss the topic on bundles. The map from Y to X continuous map, any continuous map is called a bundle map, and it is object of the slice category. It is object of the slice category. Top slice X. Objects are the maps bundles from Y to X. And arrows is just maps from Y to Y prime, such that the following triangle commutes. Okay, cross section of a bundle is a continuous map S from X to Y, such that the composition P and S equals identity morphism, and this can be drawn as follows. We have a map from identity map to the bundle map. Okay, and for open U, we can form interesting object. We can first of all we can define a restriction map PU from pi P reversed over U to U, and denote gamma u of the bundle P as a set of such sections the set of all sections over the set U, and this is just an inclusion map. Okay, and we have this diagram, obviously. Horizontal arrows is just inclusions. And this is a PU and P and sections, section S. Okay, and we note that if we have inclusion V into U, then one has a restriction restriction operation from gamma U to gamma V, and also and thus gamma defines a functor from the open from the set of open sets from the category of open sets to the category of sets. Okay, and also each map P to P prime of bundles over fixed space X induces a map gamma P to gamma P prime over sheaves on X. So also gamma is a functor from the category of bundles to the category of sheaves. Okay, this was an example, and now I'll give some non-example. Consider the functor B, which associates for each U the set B of U is a set of all bounded functions. On U, and this functor is not a sheaf because if we have restrictions on each UI and these restrictions are bounded, then the function, then the collation of this function is not bounded. Okay. Another example. Example in Euclidean and space. Consider the set of functions from open U to R such that all partial derivatives of order all partial derivatives order which have order R belongs to the set of continuous functions over U. For all R is less than K. This condition is local, obviously, and hence the set of such functions are collectible. And furthermore, we have a nested sequence of subsheaves on Rn. On Rn, we have the following nested sequence: C infinity to ck minus 1, and so on. Okay, and now we can give a general definition of sheaf. We also noted that sheaf is a pre-sheaf in categorical sense. It is a contravariant factor from the category of open sets to the category of sets. Now the definition. A sheaf. A sheaf of sets F on a topological space X is a functor. F from this category to the set such that each open covering gives an equalizer. Okay, where for each t from Fu we set E of t is a set of restricted maps for any index from I, and also t restricted on UI is F of the inclusion the inclusion map. This is just a restriction, and for and for family ti from FUI, we set P of this family of maps is the set of restricted maps on intersections, and Q over Ti is a restriction over Tj to intersections. Okay, and this was a definition, and of course we can change this category set, and we can write the other category for any category. It makes sense. Okay, and now we obtained an inclusion over sheaves on X to the category of branch sheaves on X. It turns out that this inclusion has a left adjoint and we will prove this later. Okay, and now we will define separated pre-sheaf, separated pre-sheaf is a functor f such that the equalizer map E is injective. But but not necessary. Equalizer. For example, if we consider the functor B, then B is a separated pre-sheaf, but it is not a sheaf. Okay. Remark? It follows by definition that f of empty set equals one-point set. For every sheaf, for any sheaf F, it's true. Okay. Now I want to give a definition of a subsheaf. Definition. Subsheaf of a sheaf f on x is defined to be a subfunctor of f, which is a sheaf itself. And I recall the definition of a subfunctor here. Consider two functors, f from the opposite category C to the set, and G. And G is a subfunctor of f if the following conditions are true. The first one, for any C from the category C, we have that G of C is a subset of f of C, and also for all map, for all arrow, we have that G of f is f of f, which is restricted on G of C. Okay, proposition. If f is a sheaf on the space X, then a subfunctor S is a subsheaf if and only if for all open set U and for all map F from FU and for all covering of the U, we have that F belongs SU if and only if F restricted on UI belongs to SUI for all I. Prove this simple proposition. First of all, if S is a sheaf, then proposition follows obviously. Okay, and the other direction. Consider the commutative diagram. product of SUI maps to the product of SUI intersects UJ, and we have an equalizer. Sorry, and also we consider the following equalizer for F. F is a sheaf, and we can consider this equalizer. It exists, and we have induced maps because of definition of subfunctor. We have these maps. Okay, and we can consider the pullback of this diagram. Consider the pullback. SU, and SU is also limit of this diagram. That is this row is just equalizer, and prove this statement. It follows from universal properties, and consider some cone Y. This is a cone over this set, and then we have a composition. Then we have a composition, and we have the following map, and hence, as this is a limit of this diagram, then we have a map from Y to FU. Oh, sorry. This is a cone for this diagram, and we have another map, and thus we have a cone over this diagram, and from universal property of the pullback, we have this. We have this arrow. And thus, for all map such that this diagram commutes, we find uniquely map such that this diagram commutes. Okay, and thus is it is an equalizer. Okay. And now I'm going to define a direct image definition. Let f from x to y be a continuous map of spaces. Then for any sheaf f on x, then any sheaf f on x gives a sheaf which we denote as f star f on y, and by definition, this is f of this is a f of pre-image of v, or for all v from this category, and the sheaf f star f is called the direct image. And as usual, star symbol is functorial. That is, we have the following identification, and thus we have a functor sheaf from the category top to the category of sheaves, and sheaf of f is just f star. In particular, of course, if f is homeomorphisms or homomorphism.
What is the category sheaf? What are objects in category sheaf?
Okay. Thank you for the question. Category sheaf is a category which consists of sheaves as functors and natural transformations as arrows.
So these are just sheaves on one topological space, or?
Of course. We for each topological space, we can consider sheaves on this space.
Okay, thank you.
Okay, I can really I should write this. And of course, if f from x, y is a homeomorphism, then f star gives an isomorphism between sheaves on x and y. Okay. And now we can consider map U to sheaves on U, which for sheaf f sorry. Okay, which for a sheaf f gives a sheaf f restricted to U on U, and also the inclusion V into U sends to the following map. And thus, we have a contravariant factor on X. Have a contravariant factor on of X, and this factor from this one to this is true, of course, for a press sheaf, but for sheaf also. To sheaves on X or press sheaves also for sheaves. Because of the fact that sheaf lives in a local setting, this factor is itself almost sheaf, and the following theorem tells when this is a really sheaf. If we have a current of X, WK is an open current of the space X, and if for all K Fk is a sheaf of sets on WK such that Fk restricted to the intersection equals Fl restricted to the intersection for all K and L. And then there exists a sheaf F on X, unique up to isomorphism with the isomorphisms for all K. Okay. Let's prove this theorem. First of all, we should understand that F is a press sheaf. The first step, F is a press sheaf. We will write FKL for the sheaf. Fk restricted on the intersection. If we consider the equalizer of we consider the following equalizer. Okay, and if the desired sheaf f exists, that is, we have the following. Then we can take consider any inclusion, and this inclusion induces the following diagram. This diagram maps to this one. Oh. And we have a equalizer. We okay, if it exists, then for all u, we must have an equalizer, and equalizer 1, equalizer 2, and we have this unique map because of this. This is a cone. This is a cone for this equalizer, and for this cone, there is unique map like this. Okay, and hence for all inclusion V into U, we have a unique map. Fu to Fv, and thus F is a press sheaf. Okay, and the second point, F is a sheaf. Consider any covering of U. Consider any covering UI over U. Then we should form the following diagram. Oh, F, the first equalizer. The first will be equalizer. The second also is an equalizer. And the third is an equalizer. And we have vertical maps. And now we know that this one is an equalizer, this one is equalizer, this one is equalizer. And from the we can conclude that this is also an equalizer. And thus we have proved this theorem.
Right. Can you explain why the top row is an equalizer?
This one?
No, the top one.
Top. Okay, top. This because for this open covering we have that this is true. This is true for this covering.
Okay.
Okay, thank you. Okay, this is so. But there is another method of constructing sheaves on the space. We can construct this by means of sheaves, and but first of all, consider the statement which tells us that for a basis that we have an equivalence of categories where B is a category, is a subcategory of the space of all open spaces such that B is a basis of topology. This is obvious, and consider such B, and we can restrict our sheaf on this B if we have a sheaf F then we can restrict this on B and for all open cover we have the following equalizer. Thus, we have a restriction factor from X on B. Okay, now consider the next topic, sheaves and sheaves. Consider topological space X and open set U. Then this set determines press sheaf press sheaf. Which is just following. Home from V to U is just one point set if V is a subset of U, and empty set otherwise. This is a simple reformulation of such fact that there is a unique mapping from V to U, this inclusion, and this inclusion we can code with this symbol of one point set. And if V is not a subset of U, then there is no such map. Okay. This press sheaf is called representable press sheaf. And we can know this by in the following way. Okay, and now we can define a sheaf definition. Sheaf on an open set is defined to be a subfunctor of the representable functor. Okay, and also we can describe sheaf as a subset of open sets, and such that if V in S and V0 is a subset of V, then it implies that V0 in S. In particular, if we have a unique V0, it determines principal sieve. On U, which consists of all V such that V is a subset of V0. And we note that a sieve S on U is a principal if and only if the subfunctor S over representable presheaf is a subsheaf. Okay, and now we can prove the following proposition. A presheaf P on X is a sheaf if and only if for all open set U of X and for every covering sieve S on U, the inclusion IS S2 by U of functors induces an isomorphism. From this to this one. Natural transformations from the functor S to functor P is one-to-one with natural transformation of a representable presheaf over U and presheaf P. The proof.
Sorry, and what sieves are called covering?
Okay.
What is a covering sieve?
If we have a covering of U, then we can form a sieve which corresponds to this covering, and we take such a set which includes into corresponding UI. We take all V from this open V from this category such that V includes into UI for all for some I.
My question was slightly different. I was asking when we call a sieve covering. So when we say that sieve is covering you, for example. Because you say that for any covering sieve S on you, the inclusion something. So I'm asking, what is a covering sieve?
Sieve which corresponds to this for this covering of you.
So okay, so just okay.
Can I ask a question?
Yes.
So here sieve is just the cover of a fixed open set, right? This topological situation, or it is something different?
We have an open set and some covering, and in this session we can define covering sieve. And in this situation, we can consider any covering of U and corresponding the covering sieves.
All right, thank you.
Now I think the proof now is the proof is so long, and I'm not sure that I should give it. I skip it and I'll prove that proposition is the next seminar. And now I think I think we may stop in this point. Okay.
Could you please show the definition of a sieve once more, please?
The definition, and we have a set, open set U, and we can we consider the following functor, subfunctor of this functor is the following way. If
So O of U is just open subsets in U, right?
Yes. Mhm.
So choice of this S is a choice of some open cover which is closed with respect to intersections, right? In U.
No, it isn't a cover, but we choose we choose some subsets of this set, and we take all subsets of this set. So that is, if we have a V in O of U, then we should take all subsets of this set, and
So empty set S, just empty, is fine, right? For example.
yes.
I see. Thank you.
Any questions?
If I may, I have one more question. There is another approach to sheaves in terms of etal spaces. Am I right that this is complementary to your talk?
What is
the etal space is a covering associated with a sheaf. To each sheaf, we can associate, well, in sets, for instance, we can associate covering space called etal space. And we can recover a sheaf from this, well, object as well. So you didn't discuss it.
Yes, but I'll give some information on relation between sheaves and
these etal spaces, right?
Yes. Okay, later.
Cool. Thank you. Thank you.
Question from a chat.
Just discussing what is a covering sheaf. It's not a question.
Yeah, thank you. Thank you. I'm reading it.
Okay.
Maybe we can stop the recording.
I think yes.